Hello guys, my name is Michał Kowalczykiewicz, and for today I have a presentation for you with this romantic title. But first, let's start with a bit of intro about LogicBlox. Company from Atlanta in Georgia called Predictix, which merged with Infor 2 years ago, created LogicBlox. And LogicBlox is an application platform, a smart database for doing computations in big data, in massive data, in retail, for solving problems like forecasting, replenishment, or demand management. And this platform has a lot of great innovations, like, for example, in-database analytics. Because in a typical machine learning application, there are three layers. There is a database layer. Usually the programmer runs a query against this layer, and then the materialized view is processed on another layer, on the business logic layer. And then usually some machine learning tool like TensorFlow runs to get some more data, and then this data is presented on the presentation layer, so on a front end. And in LogicBlox, this is not the case, because database and business logic layer are unified under one language. So the only concept the programmer should care is not data retriever, is not database, it's the logic, and nothing more. Another interesting thing is live programming. So in LogicBlox, it is extremely easy to add some piece of code or to take some piece of code from the running application. So we have this keyword add block for adding code and keyword remove block for removal of the code. So for example, bug fixing is easy because we do not need to stop the application, apply the fix, and redeploy the application, because we could do it on the fly. And there is much, much more. For example, LogicBlox has the built-in support for predictive and prescriptive analysis. The database behind this is not a relational database. It's something called factorized database. And what is interesting about this factorized database is that it has a lot of optimization tricks which you normally see in a compiler theory. Like, for example, incremental maintenance or data flow graph. And I think the biggest achievement in LogicBlox is that it implements the concept of moving the code to the data and not the data to the code, which is important because we work with the massive amount of data. And what is also interesting here, there is much more, you could check in this paper. It has all of the keys aspects of LogicBlox explained point by point. Okay, but the most interesting things for us, at least for this presentation, is logical. LogicBlox comes with the logical, and logical, this is an implementation of first-order logic. It's a superset of the language called Datalog, and it is even more declarative than, for example, Prolog, because I know how many of you code at university in Prolog. In Prolog, the programmer still needs to care for the order of the rules he writes. But in logical, in this language, it's not important. So you could just write the rule in any order you want. The compiler will optimize it for you. Okay, so I'll just do a short tutorial about how to code in logical. And from experience, I know that it takes something like 2 months to understand it. But I'm quite sure that for you guys, for the Scala developers, 5 minutes is enough. But let's start with the simplest concept. So in logical, we have just one abstraction. And this abstraction is the predicate. And to use the predicate, first we need to declare it. And declaration of a predicate is something like a signature of a function in Scala. So we create something, we assign some types. So this is a definition, a declaration, and these types could be float, int, or something like this. And this is the example of something called entity predicate. And this entity predicate is something like a class in Scala. So we create new something called item here, and it's like a class in Scala. And there are many more kinds of declarations. For example, we have relational predicates. And in this case, it means that item is in a relation is not unique. And think about relations in algebra. So it's something like this. Also, we have the functional predicates. You can see that this, the bracket is square, yeah? We have a square bracket. And think about functions in algebra. It's the same. And we could read the first functional here as item, but each item should have a description, and this description is string. Also, we could encapsulate that kind of logic into the export clause, export section. And this export section is something like public in Scala. So thanks to this, in different parts of the code, we could relate or reference or use these predicates. And we are almost there. We have declarations. Now we need to have definitions. And with definitions, we need to define how our predicates relate to the different predicates in the system. And there are two kinds of definitions. The first one is a constraint. And you see that the arrow is from left to right. And we could read it as, if I is item, then I should have a description, and I should have a from supplier. These commas are like ends in this language. And ors, for ors, we have semicolons. Underscore is like a wildcard in Scala, and it means any. OK. And we have also the rules. And a rule is a bit different. And as you see, the arrow is from right to left. And we could read it like this. If we have two different items, and because we have a comma, these two different items have the same from supplier, and these two different items have the same SKU, that it means that these items are not unique. And what is interesting here is what I mentioned, that this SKU from supplier and inequality could be written in any order, and LogiQL will always optimize it on the fly. And before we go further, just one nomenclature, that in logic languages, not only in LogiQL, but also in Prolog, Datalog, and many others, everything what is before the arrow is called the head of the rule, and everything what is after the arrow is called the body. Yes? So in this case, the is not unique is a head of this rule, and everything else is a body. And there is also something called alias all, and it's in relation with this export section. And thanks to this, we could import some different predicates and use it here. So it's like a, let's say, import in Scala. And finally, we have a construct called block, because all of our code is written in blocks. And we could disable or enable some pieces of logic also on a runtime using this live programming trick. And there is much more. For example, there is a support for many built-in predicates, like some manipulations on strings, some basic operations on built-in types like floats, decimals, or ints. And there is this AGG predicate, which works like aggregation above some predicates. What is also interesting is LogiQL has a built-in support for CRUD applications. So if you want to write some, if you want to serve some HTTP logic, some HTTP requests, it's extremely easy to to handle HTTP get, post, push, and delete because it's written inside the language. We have many types of predicates. With this pulse, for example, we could mark that some predicate should disappear when something happens. For example, some transaction happens. And thanks to this, for example, in some HTTP request, some predicates will totally disappear from the workspace. So it's like, in Scala, it's like a local variable. OK. And we have a lot of compiler pragmas to disable or enable some warnings or errors. And there is many, many more. The question is why we use logical or why we use declarative language. So check these two formulas. Because in general, we use logical because in very beautify and concise way, we could describe the problems which we want to solve. And if we'll check now the first formula, yeah, so in the first formula, we iterate over all elements of some food set, and we multiply two predicates, cost and buy. In logical, it's straightforward. We create this functional predicate, and it's a rule, so we see that arrow is from right to left, and we use this built-in predicate for aggregation. It's clear, guys? OK, so go further. In the second formula, we see a constraint, because we have a quantifier for all. And in this quantifier, we say that for all elements in the nutrition set, we calculate something. So this is a constraint. And logical, it is also straightforward, because it looks like this. So we create some in-between predicate called total nutritions to capture this amount multiplied by. And with this, we construct the constraint for the second formula. And this is still nothing special, because, for example, in Datalog, we could do something, let's say, extremely similar. But imagine the scenario like this. Let's say that we want to treat by as a variable, and we want LogicBlox or logical to fill the values for this by predicate in that way that the second formula, this constraint, is still valid, and the t, so the first formula, is minimized. So we want to treat t as a, let's say, in machine learning language, as a target or as our objective. So it's really easy, because we have a pragmas, built-in pragmas for this, and we could just mark that by is a variable, and we want to minimize the t. And what is special now is that, for example, in the running application, we could, during the runtime, change the values behind cost or change the values behind amount, the same with the by. Sorry, the by, but with the total nutrition's low. And logical will, like this, calculate the values for by. And what is special is that logical is the first commercial language which has that kind of built-in support. Also, the optimization, yeah? We work with the massive amount of data, and we want to have some kind of tricks for parallelisation. So imagine that we want to calculate this fun predicate. So we could run calculation of this predicate on one core. We could run calculation on this predicate on a second core of our machine. And separately, we could run calculation of this predicate on different core. So almost everything could be parallelized in logical languages. And if you want to know more, Terry Halpin, a couple of years ago, wrote a really good book about logical. Check it out. If you want to know more about declarative languages, about logic languages, the concept is a bit different, as you see, than Scala. Check it out. Okay, guys? Okay, okay. And now probably you are curious why the love affair. And I see that you are a bit of anxious, some of you, because where is Scala? Yeah? We are on a Scala conference and some guy is speaking about logical. So be patient, yeah, be patient, because Scala is coming in few slides, very few slides, I promise. But now let's have a bit of more of logical. Yeah, you like it. Okay, so on the left we see a real piece of code from a real application doing forecasting, and this piece of code is doing feature extraction. It doesn't matter what it is, it's called feature extraction. And on the right, we see another snippet of code from the same application from a different file. And I think that there is extremely easy to see that there are a lot of similarities between the left code and the right code. So, for example, the heads of the rules on the first file and the second file looks the same. Yeah, we have feature F, feature key, equals description on the left and on the right. Also the bodies of this code looks pretty similar. Yeah, we have string add with some string inside, plus some dims product here and there. So the problem is that in LogiQL there is almost no reusability of code. I'll show you the more, let's say, concrete example. Imagine that we want to calculate the ABS fun rule. And this rule will work like this, that it takes a fun predicate, yeah? And it will give the absolute value of what the fun predicate gave us. So for example, if fun give us -5, ABS fun will give us 5, yeah? If the fun will give us -6, ABS fun will give us 6, the absolute value. And now imagine that the signature of the fun predicate will change, and it will have also color and style. Because maybe we want to write application for fashion retailer, for outfit retailer, who sells jeans or t-shirts, and they want to care also about color and style. And now the problem is that now we need to change also the declaration and definition in the ABS fun. So with this extremely small change in the fun predicate, we need to change almost everything regarding this ABS fun. So declaration and definition. And what is a bigger problem is we need to do many changes in different parts of the code when somewhere some different predicate references this ABS fun. So we need to do many small little changes everywhere. And if you just generalize this and just want to know why it happens, is that, for example, in Scala, we have a lot of abstractions, like classes, subclasses, lambdas, monads. But in LogiQL, there is just one abstraction, which is the predicate. And so this is our major problem, that we have just one abstraction, which is called the predicate. We do not have anything higher. So it would be great if we would have a higher abstraction, and we could treat this ABS fun like a higher order function. So, for example, if you will let ABS fun to take some predicate, and based on this predicate, give us the correct rule of LogiQL. So this is something what we would like to achieve, to not to have these problems with mini variability changes here and there. And guys, here comes the Scala. So the idea is, let's create a code generator in Scala, which will encapsulate the logic of LogiQL, or model the logic, the grammar of LogiQL inside Scala. And one of the best ways to do it is to have to model it via the abstract syntax tree. So guys, one by one, we'll just model the concepts from logical inside Scala. The major concept first, yeah? So we have the predicate. Predicate has a name, which is a string. It has keys and values, which are some sequences of types. And we have many kinds of predicates, like this pulse one or built-in. So we have some list of possible booleans, yeah? For example, pulse in, built-in, calculated in one-to-one, and so on. We have types, so we need to model the types in Scala. And in logical, we have primitive types, numeric types, and with these numerics, we have subclasses like for int, for float, and for boolean. Also, we have this entity type, which was on one of the previous slides, so it's easy to model in Scala. And when you see the ABS tree, the leaves, yeah, the leaves of this tree are called terminals. Let's call it terms. And in these terms, we have some concrete values. So not variable, not types, some generic types like float, ints, but something as a leaf in a tree is let's say concrete values. So we had variables, we have constants, and we have int constant for floats, for strings, and for decimals. And now we could do, we could prepare ourselves to build some logic. So we build formulas, the logical formulas. And the easiest logical formula is called the atom. And to build a formula, we cannot use the predicate, because predicate has, in keys and in values, it has types. And we need to have concrete things, like from the previous slides. We want terminals, so we want constants and variables. So atom, in our case, is a, let's say, concrete predicate. So predicate plus the keys and values, which are the sequences of terminals. And to build the higher formulas, we use this conjunction, so this comma, yeah, and this junction is semicolon, or these are the sequences of formulas and atoms. And finally, we had, for definition, we have a constraint and we have a rule. Yeah, constraint was from left to right, rule was from right to left, and we had a head and body. Okay, so we have everything now, except the block. So our final concept, which just takes everything and groups everything, was this block. And block has a name, has the alias, the export clause, which you saw, the clausules, and this pragmas. And now, let's go to our example. So you remember we had this, yeah, which was problematic because it was written in LogiQL. And we want to have something like this. Okay, so let's write code in Scala, which will take some predicate and will build something which is, let's say, LogiQL. So let's create a function, let's call it ABS fun, which takes a fun predicate and give us a rule. And this rule should model the LogiQL, which you can see in the right bottom of the screen. Is it clear, guys? We create a function which takes a predicate, this fun predicate, and want to build a rule which will encapsulate the logic of the LogiQL example snippet, which is on the bottom right. Okay. So rule has a head and has a body. Let's start with the head. And we have two problems here. The first is we do not have, let's say, a static amount of variables, because as in this example, we have n plus 2. We have x0 till xn and variable v. And the amount of variables depends on the signature of the fun predicate. So this is our first problem. And the second problem is we need to have some kind of the binding between the types and the variables. So if, for example, x0 will be always on the same place, in the correct place in the fun predicate and in the ABS fun predicate. So we need to have that kind of binding between types and terms. So let's define a type map, which will hold this binding, and let's calculate it in a allocate method, which will calculate on a site. So for sure, this allocate method will take some sequence of types, and in this case, it will take the sequence of types which are in the fun predicate. Yeah. Okay. So there are many possible solutions for this. We have a def allocate. We could statically, just for for this presentation, create a pool of variables with 21 concrete variables. We could do it like this because I think it's pretty ununique, pretty unique maybe, that some rule will need more variables than 21, because if it more variables than, let's say, 15, it probably needs to be refactored, and something should be recalculated and written in a different way. And then we take the types, we zip it with the variable with pool variables, and we create a map. Okay. So our type map now is invocation of this allocate function, plus we need to have two variables for, we need to have one variable for v. So type map is allocate plus this new binding between float and v. So are we ready to create the head? Head is a sequence of atoms, and here will be just one element sequence, because in a head there is just one atom, yeah, there is just ABS fun, nothing more. But the problem is that we have the predicate, and we want to have the atom. The atom, as you remember, is a predicate with concrete keys and values, no float billions, but with concrete constants or variables. So let's create on a site a method called bindKeys, which takes the predicate, which takes the binding, this map, and we could do it a bit more generic and return a lambda, which takes a term and returns us the atom. So it's one of the, let's say, possible solutions to handle this. And now our head looks like this. So it's a sequence of just one element. We use this bindKeys because we don't want a predicate, we want the atom. The ABS fun predicate will be almost the same as fun predicate, except the name. So we could just copy the fun, change the name, and we want to have the keys and values the same. And we feed this lambda with this v variable. So we have a head. Now let's do the body. So body is a formula. It's a sequence of two atoms, because we have fun, we have the comma, and we have the float ABS. And what is missing here is only the float ABS, because everything else we have, yeah? We have this bindKeys, we have allocate, we have the pool of variables, but we don't have the float ABS function. So let's do it on the side again. And I mentioned that LogiQL comes with a lot of built-in predicates, and also it has a lot of predicates for calculation of absolute value. So for example, there is a predicate float ABS for calculation of ABS for floats, the same for decimals, the same for ints. So let's again do it a bit more generic and return a lambda, which will take a type, and we'll build this unary predicate ABS. So if we'll feed it with float, it will create us a float ABS predicate, which exists in the LogiQL. Okay. So now it looks like this. It's not so extremely readable, but we'll go a bit further. So one by one. We need to create this x variable, yes, because we do not have it. We only created the v1. We want the atom for fun predicate, and we want this ABS predicate, and we want the atom, so we create it via some atom constructor. And The final and the final body is a formula, which is a conjunction, because we have the comma, of two atoms. Yeah, so we take the sequence of two atoms, and there is a lot of orchestration here, like this allocate, creation of variables, bindings, and so on. So some time ago, we created a small DSL for this language, and now that code looks like this. And I think it's clear to see that now make rule looks in Scala looks almost the same as the equivalent logic in LogiQL on the right bottom of the screen. So make rule takes a head, and this head looks almost the same like in LogiQL. And make rule takes a body, and this body looks also the same. Yeah, but we use the concrete and not the comma. We achieved this with a lot of implicit. Yeah, there are a bunch of implicits here, and this unique var, you see this object, yeah, unique on the almost on the top, on the middle. Unique var is a stream object in Scala, which could give you the indefinite amount of variables or something. So this is the wrapper. Unique var is a wrapper for Scala object, and so now we are able to write functions which will generate code in LogiQL written in Scala, and probably something like this we could do for many different computations. But at Infor we went a step further, maybe many steps further, and we started generation of whole applications. The process is called model Refinery, and how to read it. So in the past, okay, so you want to have the new LogicBlox application. So in the past, we'll just sit and we'll write everything by hand in LogiQL. And now it's a bit different. Now we have 3 inputs. So the first one is a static code, some pool of static code. It's still in LogiQL, which was written some time ago and which is almost not touched. For example, we need the code, we need a logic for handling calendar. Logic like some basic logic which you already have, for example, in Scala, like that January has 31 days. We need to have that kind of logic. Or that Monday is before Tuesday. So that kind of general logic, let's say, the universal truth about the world of retail, it was written once, and it's now in the static code and used by different applications. Second input is client-specific libraries, because for sure each application is unique, and for sure for each application we'll need to write some pieces of code still in LogiQL, because they are so unique, but it's not worth to code it in Scala. But maybe in the future we'll see, for example, that some piece of code is in this application, and in a second application we'll unify it with this DSL and add something to also generate it. And what is the most interesting input is a data model. We use a HOCON format, and HOCON is like a JSON. It's a superset of JSON. So if you know JSON, you know HOCON. And in this data model, we could model the requirements, the features, which in the applications we want to have. And in the next slide, I will show you the example. And now what happens? Now we take all of these 3 inputs, yeah, from the static code, client-specific libraries, data model. Some magic happens in the code generator, and we create the app. And this is the example of the HOCON config file. It was taken from a real application which has, I think, 121 lines. I just, want to show you just a couple of them. So as you see now, in a really easy way, let's say almost English language, we could say that for some forecasting application, we want to have a scaling with that kind of parameters. We want to have some predefined features for generation of Fourier series, or we want to calculate the trend. So we want to have a logic, the full logic, set of logic to calculate Fourier series. And maybe we want to have some logic for calculation of some metrics like asymmetric weight, bias, and so on. And I checked 2 days ago that with the whole file, with 121 lines, the model Refinery generates 6,000 lines of LogiQL code. 6,000 lines of LogiQL code, which before was written manually. So now we do not need to code everything logical because of this code generator. And just on the end, so in fact, we have a love affair in our company because the relationship between logical and Scala is a perfect fit, perfect match in our company. And just guys, on the end, the LogicBlox team is in Atlanta, in Georgia. The Scala model Refinery team is in Wrocław, in Poland. And thank you, guys. Any questions, guys? And now, who loves logical? Perfect, perfect. If there are no questions, I will be near to the coffee, so we could speak more about, not Scala, but maybe love between logical and Scala. Why not? Okay, thank you.